Okay, everybody, so what we're going to be looking at in this lesson here is something known as counting techniques. Now, counting techniques are not the same thing as a counting method, where you would say, oh, well, count by ones, count by twos, count by fives, something like that. That's not what we're talking about when we say counting techniques. Counting techniques is a way of identifying all of the possible combinations that you might be able to get in a particular situation. Like if you're flipping a coin, rolling a dice, how many times could you get a 6 in a row? Or if you roll the dice, 10 times, what are the possible combinations of things that you could get? So that's what we're kind of referring to when we talk about a counting technique. Now, counting techniques, well, at face value, they're fairly simplistic. They can get a little complicated depending on how many variables that you are adding. And you'll see an example of what that looks like here very shortly. So what we're going to be looking at here in order to figure out one of our counting techniques is we're going to be making something known as a tree diagram. And that's just a way of saying, okay, well, given this event, these are the possible outcomes. I could have this, this, or this. And from each of those individual outcomes, I could have something else. And then we would branch off from there and say, oh, we could have this, this, or this. And you'll see that the possibilities, the more you do, the more variables associated with it, the more complicated your tree looks. So let's take a look at this example. So what it says, for a fair coin, draw a tree diagram illustrating all possible outcomes for 4 flips. Okay. After we're done with the tree diagram, then we will create an ordered list showing all of the possible outcomes of those 4 flips. Now let me explain. Here in this example, you will very clearly see, well, the more times you do something and the more possibilities you have, clearly the more intricate your tree is going to look. So for a fair coin, okay, so we're going to assume for this example that it's evenly balanced, and so if I flip it 100 times, I would probably get 50 heads and 50 tails. Okay, so that's, theoretically we could say, well, the quarter is not quite evenly matched or whatever, but okay, for this example, we're going to say it's evenly balanced, so it's a fair coin. So draw a tree diagram. Now I'm going to do my best to try and fit this on here in one go. And let's see, wonder if I'm going to have enough space. Let me move that in just a bit. So I could have, if I flip a coin, we generally say we can have 2 outcomes. The coin could land on heads, or the coin could land on tails. Okay, so those are the options that we have. So if we flip it once, let's say that it landed on heads. Well, if it landed on heads, from here, if I flip it, I could again get a heads or a tails. And for each successive flip, we would get those same options. Okay, so let's say we flipped it and it landed on tails. Well, from here I could get a head or a tail. And off of each of those, we will get kind of that same branching pattern that's going to go off, because for each potential output that we had, when I flip the coin again, I could either get a heads or a tails. So here at the very first one that you see, that was the first flip. It either landed on heads or it landed on tails. And depending on what it landed on, when I flip it again, I could get a heads or tails. So if it landed on heads the first time, when I flip it, I could get a head or tails. If it landed on tails the first time, again, when we flip it, we get a head or tails. And for each time that we flip it, we could get a heads or a tails. Okay. So at this point, we have flipped it 2 times. The first row where it just says the H and the T, that's our first flip. Those are the possible outcomes when we flip it 1 time. And the middle row where it has the 2 HTs, that is the second flip, okay? So now we're going to flip it 1 more time, okay? And we're going to wind up with 1 more row and you can see the more times that you do something, the more complicated your tree diagram winds up looking. Oh, I'm running out of space here. Heads, tails, heads, tails. Okay, so that's not too bad. I knew I was going to have a hard time fitting that on there, but so these are the possible outcomes if we flip it 4 times. We flip it once so we could get a heads or tails. Then I flip again. That would be the second row, the third row, and then finally the fourth row. Those are the outcomes for our fourth flip. Okay, so these are the potential outputs or the potential things that we could see if we flipped a fair coin 4 times. Now, just imagine if we did this with the dice, even if it was just like a normal 6-sided dice that you use when you're playing Monopoly or something. There are 6 possible outputs rather than 2. So even if we did this 4 times with a 6-sided dice, you can just imagine how much more complicated that could be. So here, this is the first thing that it's asking us to do. That's part A, to create a tree diagram. Okay, so the next thing it's asking us to do, create an ordered list showing the possible outcomes of 4 flips. Okay, now I'm going to try and be rather systematic about this, so that way you can maybe predict how I'm going to be doing this. I'm going to start with the branch kind of on the left, where the first output, like if I flipped it once, I wound up with a heads. Okay, so coming down the row that you see here, that kind of diagonal row, if I flip it once, I could get a heads, a heads, a heads, and a heads. I could get heads 4 times in a row. So that is one possible output that I could have gotten. Then I could have gotten 3 heads in a row, followed by 1 tails. Then I could have gotten 2 heads in a row, followed by a tail, followed by another head. I could have gotten 2 heads in a row, followed by 2 tails in a row. I could have gotten 1 head, 1 tail, and then 2 more heads in a row. Whoa. And let's see, where are we at now? So I could have gotten a heads, a tails, a heads, and another tails. I could get a head, a tail, and then another head. And then finally I could have gotten 1 head followed by 3 consecutive tails. And all of this that you see in the first row is basically 1/2. It's the stuff that you see on the left side of the tree diagram. And you can, if you look at the way the outputs are listed, you can kind of see that we're just going down each successive branch and seeing, oh, well, these are, excuse me, these are the potential outputs. So now we're going to essentially do the same thing for the other side. I'm going to start with the tails, and then I'll follow the branches on the left all the way down. So if I start at the top, I get an individual tail. And then if I follow all the branches going down to the left, I get 3 more heads in a row. And then if I go starting at the top, going down left, I go from tails to heads to heads. But since I've already used the third heads down on the left, now I'm going to branch off to the right, and so that'll give me tails. So here I'm going to say tails followed by 2 heads with another tail. And then we'll go to tail, head, and it's just following the branches. After we use one branch, we don't keep going down it. And then I'm going to have a tail followed by a head, followed by 2 more tails, Then I could get 2 tails in a row followed by 2 heads in a row. I could get 2 tails in a row followed by a head with 1 more tail after that. I could get 3 tails in a row followed by an individual head, and finally going down everything branching to the right, I could get 4 tails in a row. So these are all of the possible outcomes that you could get simply by flipping a coin 4 times in a row. So 2, 4, 6, 8, 10, 12, 14, 16 potential outputs or combinations of outputs that you would have here. So there we go. That is what a tree diagram looks, where we just say, okay, from the first time that I do this, whatever thing that I'm doing, what are the output, what are the possible outcomes? And in this case, the only possible outcomes are heads and the tails. Okay, and then if I continue doing it, what are the possible outcomes? And so depending on how many times you do it, depends on how long your tree is and how many branches that it has. But so the more times you do something and the more outcomes that it has, the more there is for your tree and the more complicated it is going to wind up looking in the long run. So now what we're going to be discussing, and this is something that you're actually probably familiar with from elementary school actually, something known as the fundamental principle of counting. Fundamental principle of counting is basically saying, well, if we have these things, we have whatever. Usually they might, what you might be familiar with them is from word problems in the past. Maybe they say something like, you have a bag with 4 different colored marbles. What are the odds of you pulling out, like, a blue marble 3 times in a row, or something like that? So here where they're talking about Q possibilities, R possibilities, and P possibilities, well, would be like the marbles that are in a bag. They're just saying, okay, we have these things. What are the ways that they could be combined? And what we think of these as is we think of them as a series of events. And the way that we are going to calculate the number of possibilities of a series of events happening is through multiplication, where we don't add the values together. We say, okay, I have this possibility, and this possibility, and the way that we count them, like the possible possibilities that we could have, is through multiplication. And that's what you're seeing on the bottom right, where it says we take whatever the possibilities are and we say P times Q times R in this case. We just multiply them together and see what we get. Okay, so now that we have what the fundamental principle of counting is, and that's what it is, saying we take the possibilities that we have and we multiply them together. Okay, so here is a perfect example, and this might be something that you have experienced because you are generally enrolled in about 7 classes here at school, but in this case, well, I don't know, we have 6, so maybe you have senior early release, I don't know. So grades at a college consist of these letters, okay, and I have no idea what they might be. A, B, C, D, and F are pretty obvious. W is probably going to be like withdraw, like I can't handle this, I have too much on my plate, so I withdrew from the class. Okay, so those are the grades that you could have. Well, in college, you're not necessarily going to be taking the same number of classes that you do in high school. In this case, you're taking 4 classes. Okay, so if you have 4 classes, let's call them math. Obviously, my bias, I'm going to put that first, and then we could say science and history and English. Well, we have 6 potential grades that we have here. We have 6 potential grades here, 6 potential grades here, and 6 potential grades here. Because, well, you could get an A, a B, a C, a D, or an F, or you could withdraw. So those are possible grades that you could get for any of those 4 courses. Now, the fundamental principle of counting says Well, if these are the potentials, we might say, in the definition, they call them P, Q, and R. But P, Q, and R can be anything. I could say M for math, S for science, H for history, and E for English. They're just random variables that you could pick anything that you wanted to. But the fundamental principle of counting says we're going to take all of these things and multiply them together because these are the potential outputs that we have. So this is the same thing as saying 6 times 6 times 6 times 6, or 6 to the fourth power in this case. And 6 to the fourth power in this case would be 1,296 possible grade combinations. Grade So that's essentially the way the fundamental counting principle works, is we say, okay, these are the possibilities. For each class, I have 6 potential grades. So between the 6 potential grades 4 different times, we say 6 times 6 times 6 times 6, or in this case, 6 to the fourth power because we're just multiplying the same number 4 times. And 1,296 possible grade combinations. Your widths, I don't know. Just imagine how that's going to look if you are doing like 32 numbers for the lottery. So this is another kind of word problem situation that you might have seen in elementary school, but usually they say like, little Johnny or Susie has, 3 hats, 2 shirts, and whatever, and then to say, what are the possible combinations, okay? Same exact idea. A businessman has 5 shirts, 7 ties, 4 pants, and 3 pairs of shoes. Assuming that everything works together, so I don't know. He's dressed by a fashion designer, and every possible combination works. So nothing clashes with anything else. Okay, so here are the combinations. We have, let's see, we have shirts. So I'm going to call that S. We have ties. We have slacks. I'll call those pants. I'll say P for pants. And shoes, well, that would be another F. Let's call it F for something that goes on our feet. Okay, those are the different things that we have. Okay, so I have 5 of these. I have 7 ties. I have 4 pairs of pants. And I have 3 things that go on my feet, 3 shoes. And so the fundamental principle of counting says take these things and multiply them all together. And so that would give you 420 possible combinations of outfits. Okay, and so that's essentially all you're doing there. Identifying how many variables do you have. In this case, I have 4 variables, and each one has 5 different, or each one has a different number of entries. So there's 5 shirts, 7 ties, and so on. And because we're combining them in different ways, we say, oh, there's going to be 420 possible combinations in this case. Now here, this one is a rather interesting question. Okay, number of combinations. Okay, so same idea. We're still looking at the fundamental principle of counting, but the really challenge is going to start to be, okay, can you identify all of your variables and numbers correctly? Okay, so if I was born March, April, or May, after the 19th, but before the 30th, after 1949, but before 1981, how many different month, day, and year date combinations would be possible for my birthday? Okay, so here we're talking about months, we have days, and we have years. So those are the 3 entries. Those are the 3 things that we're counting. Okay, well, how many of each one do we have? Okay, looking at the number of months, well, March, April, May, there's only 3 months that we're looking at here. Well, how many days do we have? take a moment, pause the video if you need to, and think about it. How many days would there be between the night after the 19th but before the 30th, and see how many you get? And the answer would be, well, there are 10 days that are after the 19th and before the 30th. So again, if you want to pause it to figure out, well, how many years there are, go ahead and pause the video and think about it for a second. And when you're done, come back. But if we're being born after 1949 and before 1981, then that tells me that there are going to be 31 years. So the fundamental principle of counting says we're going to take each of these possibilities, multiply them together, and in this case we would have a total of 930 possible combination of dates. Okay, and I think we only have one more example here to look at. And again, this one very much reminds me of the kinds of questions that I saw in elementary school and middle school. Here we're saying how many ways can 3 numbers be selected from the numbers 0 through 19 if a replacement is allowed and B, a replacement is not allowed. Now the way that I remember this type of question is, again, going back to a marble. Say we had 3 different colors of marbles, okay? Well, you'd reach your hand in blindly and you'd pull a marble out. Okay, well, if replacement is allowed, we would put the marble back in the bag. And if replacement isn't allowed, well, we'd keep it out of the bag, and then that would change the number of possibilities that we have. Okay, so in this case, we have, let's just say we have 3 numbers. So we have number A, number B, and number C. I don't want to call them 1, 2, and 3 because we're, you know, they might not be those numbers. We just have 3 different numbers. We call them A, B, and C. And if I have and let's make sure this is example A that I'm talking about. If I randomly, I don't know, pick, let's say they're all folded up on a piece of paper, and I reach into a bowl and I pick out a number. Well, if I replace it, then each time between numbers 0 to 19, that means that there's 20 numbers in the bowl each time. So no matter what, in the first example, there are a total of 20 numbers each time that I am picking. So the odds of me picking those 3 numbers anytime, in this case we would say 20 cubed, or 20 times 20 times 20, and here we would get 8,000 So if we, you know, we have 3 draws, right? Any 3 numbers that we're picking 3, we're drawing 3 times. So if we draw a number, okay, I got this number, put it back in the bowl. Draw another number, okay, I got this number, put it back in the bowl. So each time that we're drawing, there's 20 potential numbers that we could have. So that tells me that if I keep putting the numbers back, and there's a total of 20 each time, well, there's 8,000 possible combinations. All right, so let's take a look at the second one. All right, so we still have pick A, pick B, and pick C. There's 3 picks that we can do, but in this case, the replacement is not allowed. And this is very much kind of like the way maybe the lottery works, because they have little balls that come up and they don't put them back in the little hopper to see how many, you know, combinations there could be. So let's say, okay, the very first draw, there's 20 numbers in the bowl, so there's 20 possible values that you could pick. Well, whatever that first number is, if you don't put it back, now there's only 19 numbers the next time that you pick. And if at the third time I pick a number, I haven't put, so I've picked twice and I haven't put either of those numbers back. The third time that I pick a number, now there's only 18 values with which to choose from. So again, fundamental principle of counting says out of the possibilities that we have, to find out how many of them there will be, we take those numbers, multiply them together, and in this case we would have 6,840 possible number combinations. Okay, so those are essentially what we're talking about when we say counting techniques. We're trying to determine, okay, well, how many things am I looking at, And does each thing have the same amount, or are they different? And whatever they are, however we identify the number of things that we have and how many of each of those things there are, the fundamental principle of counting says, well, to find out the combinations that there would be, we're going to multiply them together. So again, as always, if you've had questions about anything during the presentation, please make sure you write them down in your notes, bring them to me in class or in tutoring, and I will be happy to help you. But until then, guys, thanks for watching, and we'll see you soon.